A prospector can outfit himself in various ways according to his means and the minerals that he seeks. Equipment can be used in many ways and its effectiveness depends in large measures on the versatility of the operator. For example, the radiation counter, of which the well-known Geiger counter is one, not only can detect radioactive minerals directly but indirectly can do more. If placer deposits contain both gold and a heavy radioactive mineral like monazite, the radiation counter can lead to the gold concentrations by detecting the monazite that is concentrated with it. In this chapter, we will focus on prospecting of radioactive minerals and their distribution in India. The following topics will be discussed, including the methods of prospecting for radioactive minerals in India, uranium deposits and distribution in India, thorium deposits and distribution in India. A prospector can outfit himself in various ways according to his means and the minerals that he seeks. Equipment can be used in many ways and its effectiveness depends in large measures on the versatility of the operator. For example, the radiation counter, of which the well-known Geiger counter is one, not only can detect radioactive minerals directly but indirectly can do more. If placer deposits contain both gold and a heavy radioactive mineral like monazite, the radiation counter can lead to the gold concentrations by detecting the monazite that is concentrated with it. In this chapter, we will focus on prospecting of radioactive minerals and their distribution in India. The following topics will be discussed, including the methods of prospecting for radioactive minerals in India, uranium deposits and distribution in India, thorium deposits and distribution in India. A good understanding of the geochemical behavior of nuclear fuel metals, their morphology and geological processes favorable for and responsible for their formation have facilitated sustained efforts in the exploration for these. Significant from the exploration point of view, the time-bound characteristic of uranium deposits. Major uranium deposits are found in rocks of lower to middle Proterozoic, Permo-Carboniferous, Mesozoic and Tertiary ages. 5 major orogenies at 2500, 1800, 1350 and 30 million years have helped in recycling of uranium by magmatic anatectic reworking of the pre-existing rocks and through the action of groundwater, leading to a variety of deposit types. Recognition and characterization of these geological environments is the first stage in the exploration program. Exploration and prospecting techniques. The exploration techniques are principally based on physico-chemical properties of uranium and associated elements. Uranium and its daughter elements are undergoing constant disintegration and releasing alpha and beta particles and gamma radiation. Characteristics of daughter elements Bi214, Ra226 of the uranium-238 series indicates the presence of uranium. There are a number of uranium exploration techniques, direct and indirect, having advantages and disadvantages. The combination of techniques is used such that the limitations of one are supplemented by the advantages of the other. The results of indicated methods like remote sensing, geophysics and geochemistry must be taken in consideration. The exploration geologist should know the advantages and limitations of each method. Coming to the geological mapping. For exploration purposes, published maps of the area may be used, or if none is available, mapping may be required. This may be done using remote sensing techniques. A suitable map scale for such an exercise is 1:50,000. Maps of this scale may help in locating the most probably and potential geologic environments of uranium mineralization. In the initial stages of the exploration program, geological maps help in the interpretation of geophysical and geochemical anomalies. In the advanced stages of exploration of more detailed maps, perhaps on scales of 1:2000 or 1:1000 may need to be prepared. Number 2 is remote sensing. Remote sensing refers to the gathering of information about the earth without actually coming in contact with it. Coming to the aerial photography, satellite imageries, gamma ray spectrometry, all are remote sensing techniques using different wavelengths of the electromagnetic radiation. Instruments used are scintillometers, photography cameras and sensors or scanners. Aerial photographs and images are used for making thematic maps. Drainage patterns, erosional features, rock types, superficial deposits, igneous extrusives and intrusives, altitudes or attitudes of beds, fold axes, faults and joint planes can be mapped and relationships studied so that sufficient information is gathered. Number 3, airborne gamma ray spectrometry. Radioactivity emanates mainly from uranium, thorium and potassium. 99% of gamma radiation are attenuated by 30 centimeter of rock or 45 centimeter of soil. Therefore, the success of this method depends upon rock exposure. Radiation detectors used in gamma ray spectrometry are scintillation counters, which are mounted on aircraft flying at about 120 meter. Flight lines are spaced 1 to 5 kilometers apart for reconnaissance surveys and 250 to 5,000 meters for detailed surveys. The amount of radiation detected reflects the size, shape and source of the intensity. Contour maps of both the grounds are prepared, which reflect the lithology and other characteristics of the host rocks. These anomalies later used for ground follow-up surveys. The superposition of gamma ray contour on geological map makes a meaningful contribution to the exploration program. Number 4, ground radiometric surveys. Radiometric surveys measure the distribution of 3 radioactive elements including uranium, thorium and potassium in the Earth's crust by recording the gamma radiation emitted during the decay of these elements. Approximately 90% of measured gamma rays are received from the top 30 centimeter of the ground. These measurements enable the interpretation of rock and soil types. Once an anomaly is identified using airborne methods, a handheld or jeep mounted scintillometer or GM counter is used for detailed surveys. This is the most common and cheapest method of uranium exploration. Ground radiometric surveys are most effective where rock exposures are available. Number 5 is radon measurement. The decay series of uranium produces radon, that is Rn-222, which has a half-life of 3.82 days. By emitting an alpha particle, it decays Bi-218. The detection of radon serves as a useful pathfinder for uranium and is possible through a variety of alpha particle detectors. Faults and fractures often serve as conduits through which radon issues. Hence, These surveys are capable of delineating these structures in soil-covered terrains. Though sensitive, this method is subject to diurnal changes. Number 6. Geochemical techniques. Sensitive methods of geochemical analysis can detect uranium concentrations in ppm or ppb in water, rock or soil samples. This makes it possible for analytical methods to be applied at both the reconnaissance and detailed stages of exploration. Stream or spring sediments and plants may also be analyzed for their uranium content. Geochemical surveys help in identifying the primary and secondary halos around uranium deposits. Hydrogeochemical surveys are suitable in areas of scanty outcrop or thick overburden. Stream sediments samples help in zeroing in on the target. Usually second and third order streams are sampled. The method is especially useful in forested and mountainous regions. Number 7. Geophysical techniques. Geophysical methods are used in conjunction with airborne gamma ray spectrometry for both reconnaissance and detailed surveys. Geophysical techniques are helpful indirectly since they help in the identification of major rock types. A clue to the possible concentrations of uranium can be obtained by the presence of rocks which are either host to uranium deposits or are sources of uranium. Gravity, magnetic, electrical or seismic methods may be used to bring out the contrast in lithology and help in locating faults and dislocations, sulfide and altered zones and unconformities. Number 8 is exploratory drilling. Once an anomaly has been deciphered with a fair level of confidence, it is explored by drilling. The boreholes may be of coring or non-coring type. Drilling helps in the precise location and sampling of the ore zone. The boreholes are logged in respect of lithology, resistivity, IP, magnetic susceptibility, neutron and gamma rays to get the maximum information about the prospect. The borehole samples are studied in the lab to determine the ore mineralogy and gangue mineralogy. Radioactive minerals are discrete minerals of uranium and or thorium as exemplified by uraninite of uranium and thorite of thorium. Besides, they include those in which either uranium or thorium or both occur in notable quantity, like the minerals of rare metals, that is NBTA, Li, Be, Sn, W, etc. and rare earth elements or REE from La to Lu, Y. Types of radioactive minerals. Radioactive minerals are broadly divided into primary and secondary discrete minerals of uranium and thorium, and nearly 200 such minerals are known. The primary minerals are those formed directly from magmas, hydrothermal solutions and groundwater. Secondary minerals are formed due to remobilization of elements from primary minerals, their transportation in solution, and latter precipitation due to oversaturation in oxidizing or supergene environment. The most common primary minerals of uranium are uraninite, pitchblende if microcrystalline, oxide, coffinite, silicate and brannerite, complex oxide. In these, uranium occurs mostly in U4 plus state, besides some U6 plus in pitchblende. Secondary minerals of U6 plus uranium occurring in supergene conditions are many, nearly 180, in which uranium occurs entirely in the U6 plus state. Coming to the location and identification of radioactive minerals. Radioactive minerals, due to their occurrence usually in very low content, that is less than 1% in rocks, are difficult to locate and identify by normal megascopic and microscopic techniques used in identification of rock forming minerals that occur in major to minor quantity, that is more than 1%. However, the intrinsic property of radioactivity resulting in spontaneous emissions of alpha beta particles and gamma rays of radioactive minerals is taken as advantage for their location as well as estimation of the contents of EU, U and TH. Thus, locations of radioactive minerals in a rock sample is done by the technique of radioluxography, that is RLX, or solid state nuclear detection, that is SSNTD. The latter a modified easy version of the former. Generally, these methods are used for identification of primary minerals for secondary and metamixed crystal structure damaged due to the bombardment of radiation from radioactive minerals, as well as primary minerals. The techniques of X-ray diffraction, that is XRD, is used. After a pre-concentration of the radioactive minerals using heavy liquid and magnetic methods, occurrence of radioactive minerals. Radioactive minerals occur in very low content in different rock types, for example in magmatic or igneous rocks around 2 ppm in the crust, and number 2 sedimentary rocks, number 3 metamorphic rocks of low grade like phyllite and schist. In the magmatic rocks, they usually concentrate in acidic plutonic rocks which include granitoids, pegmatite, and volcanic rocks like rhyolites and acid tuffs. Radioactive minerals like monazite and zircon are used in placer derived from such magmatic rocks. Amongst the sedimentary rocks, sandstones, pyrite bearing quartz pebble conglomerates, and phosphatic and carbonaceous rocks are good hosts for uranium minerals. Low grade metamorphic rocks like phyllite and schist subjected to metasomatic alterations involving addition of volatiles within the structurally weak zones are loci for the uranium minerals. Thorium minerals occur generally in acidic igneous rocks and high grade metamorphic rocks and placer derived from these rocks. Major types of uranium deposits based on the geological setting and economic significance. The uranium deposits in India occur in following main types. Number 1, hydrothermal or vein type. Number 2, sandstone type. Number 3, unconformity proximal type. And number 4, strata bound carbonate hosted type. Number 5, other type. Majority of these resources occur in following 3 uranium provinces, starting from Singh uranium province, number B Mahadek uranium province, C Kadappa uranium province, coming to the first, that is Singh uranium province. This province is located in the eastern region. All the deposits presently being exploited such as Jaduguda, Narva Pahad, Turamadi and Bagjata occur in this province. The other deposits in this belt are Mohuldi, Nandap, Rajgaon and Garadi. All these occurrences are of vein type. This province was well known during pre-independence period for its mineral wealth, particularly copper deposits. Soon after the formation of AMD, radiometric surveys were concentrated in this province where many copper deposits were known. This survey had resulted in identifying uranium mineralization at many locations, some of which have turned out to be economically viable deposits. The uranium occurrences are spread over 180 km long Arcuate Singhbhum shear zone, and important deposits are as follows. A. Jaduguda, located in East Singhbhum district. It is the first place where exploration followed by exploratory mining was undertaken. Soon after, exploitation was undertaken by UCIL in 1967. Mining is still in progress and mineralization has been found to continue beyond 900 meters vertical depth. Here, the mineralization is associated with conglomerate and chlorite cysts of Singh group of Proterozoic age. B. Bhatin, it lies 2 kilometers west of Jadugura along the Singh shear zone. Mineralization is associated with brecciated quartzite and biotite chlorite schist, which are highly sheared. Mining is in progress. Number C. Narva Pahar. It lies 10 kilometers west of Jadugura along the Singh shear zone. The host rock for uranium mineralization is chlorite quartz schist, and the mineralization is spread over 2000 meters strike length. Currently, this deposit is under exploitation by UCIL. D. Turam-D, a cluster of deposits, Turam-D East, Turam-D South, Turam-D West, Kerua-Dulguri occur in proximity to each other at Turam-D, located nearly 20 kilometers west of Jadugura. Uranium mineralization is associated with chlorite quartz schist. Mining of Turam-D East deposit is in progress by UCIL. E is Mohlu-D. It is located 5 kilometers west of Turam-D. The host rock is tourmaline bearing quartz schist, quartzite and chlorite quartz schist. Mineralization is established over 1 kilometer strike length and within a vertical depth of 250 meters. F is Bagjata. It is located nearly 25 kilometers southeast of Jadugura. Uranium mineralization is hosted by quartz chlorite biotite schist. The mineralization is spread over 450 meters strike length with a vertical persistence of 260 meters. Based on geological favorability criteria, surveys were initially targeted to Mahadek sediments of Cretaceous period. This resulted in identifying following deposits. Number 1, Domia Siat, located in West Khasi Hills district, Meghalaya. It is a sandstone type deposit in which mineralization occurs in lower Mahadek arcosic sandstone with abundant carbonaceous matter and pyrite nearer to the granitic basement contact within a vertical depth of 50 meters. Resource estimation was jointly evaluated by AMD and UCIL during 1993, and the deposit is ready for exploitation. Number 2 is Wakin. Wakin is located 10 kilometers west-southwest of Domia Siat in a similar geological setup. The mineralization occurs over a large area on both banks of Wahabli River. Exploratory drilling is presently in progress only in the northern block. A number of other encouraging blocks around Wakin like Wahakut, Waiting, Lostoin are also available for exploration. The following are other encouraging uranium shows located in northeastern region. A is Anek, West Garo Hills district, Meghalaya. Uranium mineralization occurs along fractures in shear granite. Secondary uranium minerals like autunite, meta-autunite, uranophane and beta-uranophane are visible in the outcrop. Number B, Kaunala, West Siang district, Arunachal Pradesh. Uranium mineralization is associated with magnetite bearing quartzite of middle Proterozoic period. Uraninite, branerite are the uranium minerals identified. C. Jamiri, Kameng district, Arunachal Pradesh. Significant uranium occurrences are recorded near Jamiri village in philitic quartzite. Uranium minerals like uranophane, beta-uranophane, uraninite and branerite occur as disseminations and stringers. Third is Kadappa Uranium Province. This province is located in the southern and south central regions. It contains the Proterozoic unconformity related uranium deposit at Lambapur, Pedagattu in Nalgonda district, Andhra Pradesh. The Kadappa basin also hosts a unique strata bound uranium deposit associated with siliceous dolostone at Tumalapalle in Kadappa district, Andhra Pradesh. Some of the uranium occurrences identified in southern region are: number 1, Tumalapalle Rajkuntapalle. It is located 12 kilometers south of Pulivendla in Kadappa district of Andhra Pradesh. The host rocks are phosphatic, siliceous dolostones of Vempale formation of Kadappa supergroup resting on Archean granite gneisses. It is a unique type of strata-borne deposit hosted in carbonate rocks and occurs over 6,600 meters strike length and within a vertical depth of 275 meters. Number 2 is Gogi. It is located in Gulbarga district of Karnataka. The host rocks are deformed limestones of Bhima group and the basement granites. It is a structurally controlled vein type of deposit and occurs over 2000 meters strike length and within a vertical depth of 180 meters. Besides the above, number of uranium occurrences are located along the fractures in the basement rocks at Mullapalle, Sanipayat, Sundapalle, Madireddy Garipalle in Kadappa district, Andhra Pradesh. In addition to uranium, rare metals occurrences were associated with alkaline rocks of Tamil Nadu at Sevattur, Pakandanadu and Kulampatti, Narlapatti, Pungurthi in Salem district. Radiometric surveys in southeastern part of the country was initiated in the early 50s. Initially, emphasis was given to locate vein-type uranium mineralization in the basement rocks. During 1990s, however, with the changing concept of uranium mineralization, radiometric surveys led to the discovery of unconformity-related uranium mineralization near the unconformity of fertile Mahbubnagar granite and overlying Sri Salem Benganapalle quartzite in the northern part of the Kadappa basin. Subsequent detailed investigations including borehole drilling resulted in the delineation of important deposits in southeastern region. These are: number A, Lambapur. It is located in the Nalgonda district of Andhra Pradesh at a distance of about 140 kilometers southeast of Hyderabad. The mineralization is hosted by Sri Salem quartzite and the basement granite in the proximity to the unconformity between them. It is a flat-lying deposit with a vertical depth of 45 meters. B is Pedagattu. It is lying in very close proximity to Lambapur deposits. The uranium mineralization at Pedagattu occurs in an exactly similar geological setup and is spread over an area of 4.5 kilometers into 1 kilometer. Entire mineralization occur within a vertical depth of 60 meters. Placer deposits of thorium. Some common minor primary constituents of igneous rocks carry uranium and thorium in isomorphous substitution for calcium. Some REE and other elements, monazite, apatite, zircon and sphene are some of the most abundant minerals belonging to this category. Most of these minerals are resistant to alteration, but they differ greatly in their resistance to attrition during their transportation with clastics. Monazite, apatite and xenotime are most easily reduced by attrition, but under favorable conditions these minerals become enriched in sands and gravels which have been transported short distances. They are found frequently in heavy mineral resistate fraction of terrestrially deposited clastics. Hence, stream and beach monazite bearing placers are found in many parts of the world. Zircon, which also carries a large portion of the uranium and thorium contents of felsic rocks, is a common constituent of the resistate fractions of all kinds of clastic sediments. These resistant minerals, monazite, apatite, xenotime and zircon, may be removed from erosional terrains of the igneous rocks and become concentrated in placer deposits in environments where rocks destruction by decomposition is predominated over that by disintegration, viz. The tropical climate zones. The thorium content of the minerals contained in these places is considerably greater than the uranium content. Therefore, the deposits are classified primarily as thorium bearing placers. Monazite is the chief source of thorium in the world, though it is the constituent of some granites and pegmatites. Such sources are not economically workable. Monazite is concentrated by weathering into economically workable deposits in beach sands in the coastal tracts of Australia, Brazil, Ceylon, Malaysia and India. India possesses the largest deposits of monazite in the world. Sands on the Florida coast are reported to contain 0.09% monazite. Beach sands of India average 2 to 5% monazite. Elsewhere in the country, black sand deposits occur in the coastal tracts of Valtair, Bimlipattanam and Narsipattanam. A good understanding of the geochemical behavior of nuclear fuel metals, their mineralogy and geological processes favorable for and responsible for their formation have facilitated sustained efforts in the exploration for these. The exploration techniques are principally based on physico-chemical properties of radioactive elements. There are a number of exploration techniques, direct and indirect, having advantages and disadvantages. The combination of techniques is used such that the limitations of one are supplemented by the advantages of the other. The results of indicated methods like remote sensing, geophysics and geochemistry must be taken in consideration. The exploration geologist should know the advantages and limitations of each method. Thank you very much.